Hello, hello. This is one heck of a chapter in a sense. It's big, lots of stories, lots of interesting things. Um, it's quite cognitive, which means it's not part of my tradition. Um, so we will skim through the chapter, although I can't really improve on what the chapter covers because the author knows his stuff. And again, this is cognitive. But I have provided you uh, with a plethora from the Three Amigos, by the way, of links. I used all of these when I taught this course live. A few of them have died. I think I've gotten rid of those. And these are what's left. My recording software on my preferred computer just turned on me and will not record audio from videos that I play on screen. And so I'm on a computer I'm a little unfamiliar with. This happened the last time I taught this course too. I was like part of the way through the course, and all of a sudden, my preferred computer would not record audio, but the non-preferred computer continued to go. So I'm assuming this will work a-okay. So let's look at a few of these links because, well, let's look at the chapter. Right? We'll look at the chapter for a second. How stimuli guide instrumental action. And we started dealing with some of this back in chapter 7, as the author points out. And, SDS delta is an issue again. Some interesting stimuli here. And peppered moths are going to become an issue again. Let's take a look. By the way, during the time these data were collected, technology changed quite a bit. So here's the bird, and there's the displays. And by 2002, we're definitely using computers. So this also should remind you of Richard Dawkins and the peppered moths, and whether you can see the target in the noise. Moths that are easier to see, the bird is more likely to peck at. And if this were the real world, that would be natural selection, which we dealt with in the last chapter. And the moths that were easy to see are going to start being selected against. And that could shift what moths look like in the real world. And there's cryptic moths because they blend in. In a sense, it's not their choice; they just blend in. And polymorphisms. This is all pretty familiar, largely from the last chapter. And yes, here we go. Animal cognition. So let me say that in the modern era, these displays are usually computerized. But some of this research goes back to a time when computers could not do that. So you will see the text refer to slides. And slides, there were often projectors back there, and they would project images on those. It would be milk glass. It would be white, but when you project it from the back, you would see what was projected. The other thing that would be used, and I couldn't find a picture of it, but there would be these rectangular units of multiple light sources, and at the front end of these light sources, you could cut a negative out, a photographic negative, and insert it, and then shoot light through it, and that would be projected often on the kinds of keys that pigeons would respond to. And pigeons are very popular in this chapter because they live a long time, they have really good vision, and they have good color vision too. Herrnstein is important to me. There we go, a long series of color slides. So this is back in 1976, and believe me, computers back then could not easily do this kind of research. And they took photographs. They went out into the real world and they took photographs. And to save money, when I was in grad school, I didn't print things. I saved them as slides. And I would bore the heck out of you by showing you my slide collection. And so I can imagine Herrnstein having zillions of slides and of different categories. And I like the Margaret category. So you had trees and you had water and you had Margaret. And the pictures are on the next page. There we go. So there we go. So vegetables, buildings, pavement, and Margaret. And the animals learn this pretty regularly. Oh, look! Oh my God! I had one of these Volkswagen. I drove cross country in that baby. That was life-threatening. And generalization is important here, and categorization. And people were complaining, well, the animals have had experiences with trees and roads and stuff. And Herrnstein said, oh yeah, have they spent much time on coral reefs under the ocean? And he did that. And they could do that. And they could do Monet and Picasso. And pigeons, right now, they can do mammograms about as well as trained physicians. Why is Iowa marked? I don't know, I visited Iowa and I went to that campus, and it's a really, really impressive academic institution. And more pictures, more slides, depending on the year. So there's so 88. They could have been using a computer, but they were probably using slides. And they had categories, and the pigeon had to peck the appropriate key for the appropriate category. And that's not Margaret, but those are humans. And cars and chairs and cats and flowers. Pigeons are quite clever. And categories, and they approved cross categories, percent correct. And then they did a transfer test using novel slides, and they nailed it. Those amazing pigeons. And different categories, as you might imagine. It's harder to learn something with a lot of different stimuli, but you do get the gestalt, the big picture, and you generalize well from that. And Rescorla and Wagner is back, and there are theories about how the animals do this. One is feature, where they look at features and decide something is something because they have certain like whiskers on cats, and therefore it's a cat. And I don't know how they decide on Margaret, although she is bipedal. And yeah, I'd take that challenge. It's you have category A and category B, and you have to figure out how this turned out. 2014, this is almost certainly done with the computer and not with slides. And prototypes is another way you can solve things. And there's a cute piece of research. You can't manipulate Margaret, but you can have these stick drawings of faces and manipulate different features independently to figure out what the animal's looking at. And then there are exemplars where there's like a gold standard against which you're comparing other things. I think I'm about to go to some of my videos. Yes, we'll come back to stimulus generalization gradients in a bit. So back here. Now, I mentioned this before. World War II, WW2, Skinner was trying to help the military. And this is Skinner pigeon bombs. And just let this wash over you for a bit. Some of these are appropriate, some of them are not. Let's look at this MIT figure here, because MIT, they usually know what they're doing. So, yeah, there's wires. And on the left, the front dome has been opened. These are optical elements that take the real world and project them onto these. Again, it's like milk glass. So if you, it's semi-transparent, you project an image on here, and the pigeon, which you can see being loaded in here, gets to see all three of these. So the animal is looking at triplicates. Whoops. Did not mean to do that, so I will undo it. Let's see what else is interesting. I thought I had more interesting pictures here, but somewhere there must be a picture of how the pigeon. Nowadays, you would expect that this would work based on touch screens. That's not how it worked back in Skinner's day. This is kind of close. So the pigeon had a rig on. It wasn't this extensive, and it was actually connected to its head. So if there we go. So if the pigeon looked right, the wire connected to its head would pivot through this hole, and the wire would contact one of four contacts. So if it looked right, then the wire on the left, the right wire, would get hit, and the bomb would start moving in that direction. And if it looked left, the left wire would get hit, and electricity would flow, and it would go that way. And then you also had up and down. So one pigeon, three projections, and the pigeon would track away at what it was seeing. And you don't know what ship the pigeon is going to see. So to do this, they had to assume that the pigeons would generalize to the appropriate stimuli. So there's pigeon bombs. This never went into service, but during World War II, Skinner was quite literally working on this. Whoops. Let me undo that. I'm being punished for not understanding this this system. Okay, so something else that actually was used, and this is pretty grim. Dogs were trained to run up underneath tanks. Soviets did this one. And as you might anticipate, it was not a good outcome for the dog or the tank. They had bombs attached to them, and they were trained to run under tanks, and then it would explode, and not to be outdone, we did it too. So it was not a good outcome for the dog. And bats. You may or may not know that we firebombed Japan quite a bit, and their buildings were wood, and their roofs were pretty easy to set on fire, and we killed a lot of people with firebombs. And here the idea was they were going to, and they did, they attached incendiary devices to bats, and they were actually flying them to Japan to use them, but the atomic bomb got there first. And if you release bats in the daytime, they don't like that often, so they go and look for a place to roost. And they would go. The plan was they would go under the eaves of Japanese homes, and then later that night, the incendiary device would go off, and we would burn a bunch of people. That came closer than the pigeon bombs, but it still was not used. And dolphins and sea lions in the Navy. The good news is nobody is getting blown up here, but the animals are trained to identify things, and sometimes attach devices to ships so that we can track them. We don't. It wasn't like the dogs. We didn't blow them up. Our dolphins and sea lions. This is pretty amazing, and you're going to see some pretty amazing rats here. So this is a TED Talk. And earlier you heard me talk about condition reinforcers, and the book did too, and training dogs with clickers. And I mentioned that surgeons were using clickers to train other surgeons to tie knots. That's used here. This is a long talk. We're not going to look at much of it, but I vote it's worth your time. And he looks like Spock from Star Trek.
You want style, but you need a great deal. Get it all with a Toyota certified used vehicle.
So he starts talking about how he likes rodents.
By detecting landmines.
Look at that.
And tuberculosis.
Look at that rat. They grow them big in Africa. So there are a lot of landmines there. And rats have pretty good olfactory systems. So the rats were trained.
As a child, I had two passions. One, rats engineering product development, and in a linear extracting and manufacturing mode. We chose rats. Why would you choose rats? Because aren't they vermin? Well, actually, rats are, in contrary to what most people think about them, rats are highly sociable, sensitive creatures. And actually, this is our product, what you see here. There's a target somewhere here. You see an operator, a trained African, with his rat in front, who actually sweeps the tree in all kinds of experiments. Rats have more genetic material allocated to olfaction than any other mammal species. They're extremely sensitive to smell. Moreover, they have the mechanisms to map all these smells and to communicate about it. Now, how do we communicate with rats? Well, we don't talk rats, but we have a clicker, standard method for animal training, which you see there. A clicker which makes a particular sound with which we can reinforce particular behaviors. First of all, we associate the click sound with the food reward, which is mashed banana and peanut with the hole. And actually, the animal learns to walk on a leash in the open and find targets placed blindly, and transfers the skills to these three Mozambican fellows, currently normal, $2 per square meter. 1,000 people last year that walked on a landmine. But worldwide, last year almost 1.9 million died from tuberculosis as a first cause of infection. Especially in Africa, where TB and HIV are strongly linked, there is a huge coming problem. Microscopy, the standard WHO procedure, reaches some 40 to 60% reliability. In Tanzania, the numbers don't lie, 45% of people TB patients get diagnosed with TB before they die. That means that if you have TB, you have more chance that you won't be detected, but will just die from TB, secondary infections, and so on. And already the old Chinese and the Greek, Hippocrates, have actually published, documented, that TB can be diagnosed based on the volatiles exuding from patients. So what we did is we collected some samples just as a way of testing from hospitals, trained rats on them, and well, see if this works, and wonder, well, we can reach 89% sensitivity, 86% specificity using multiple rats in a row. This is how it works. And really, this is a generic technology. We're talking now explosive, tuberculosis, but can you imagine you can actually put anything under there? So how does it work? You have a cassette with 10 samples. We put these 10 samples at once in the case. An animal only needs 200ths of a second to discriminate the scent, so it goes extremely fast. Here it's already at the third sample. This is a positive sample. Gets a click sound and comes to the food reward. And
So that's impressive. And when I was at UCLA, the VA just off the UCLA campus, there was a stray dog that came onto the VA, and according to the people who worked there, the dog would only respond to people who were bipolar. And a lot of the time I was at UCLA, I wanted to train dogs to sniff out mental disorders. Couldn't get any trainers. And here's cancer. I don't think this is a really good video, but and you can see it's very similar. And there's the clicker to the other procedure. And there's evidence that this works. Some people were trying to use it for COVID. These later links, I believe I will come back to later in the chapter. Okay, stimulus generalization. There's a typical stimulus generalization gradient. It's wavelengths, so you can bet that that's a pigeon, not a rat. and they were trained at 580, and you can see they still respond quite well to a little bit above 590 and down to 570, and then it drops off. There's a typical stimulus generalization gradient. Rats wouldn't do that because they don't see color. And here we have pigeons and different frequency tones, and you have an S plus of 1,000 hertz and an S minus of 950, and you can see that the tuning curve, the generalization curve, is very sharp. When you have no S minus, you get a fairly broad tuning curve, and the control is flat. But I want you to notice that the S minus here is 950. Now 950 is over here, and they were trained at 1,000. And you can see that at 1,000, they're responding pretty well. The S plus 1,000, S minus 950. But their highest rate of responding is to a stimulus they weren't trained on. And it's pushed away from the S minus. And this is called peak shift. And there's a long discussion of peak shift and why it might happen. And the concept that the S plus generates an excitatory curve and the S minus generates an inhibitory curve. And they sort of fight it out where the S minus subtracts for the S plus and can push the S plus away from the S minus. These are degrees of tilt. This pigeons again, very good high resolution vision. And this is a nice discussion. And there's Spence, and I get a little nervous because when I see Spence, I'm afraid it's going to be someone else. And Spence had a theory, and the data are fairly supportive. And there's the S plus gradient and the S. The predictive responding is pushed away from the S plus because the S minus is 570. So I hope you can see the wisdom of that. So being trained with an S minus affects your ability or your willingness to respond to an S plus. And there's lots of data on that, and there's more data on that. And again, whether the S plus is close or far away, peak shift is quite lawful, and it occurs in more situations than operant chambers. And this is same thing all over. Bright and dark things. Honig, I have a book by him somewhere. Transposition. Animal is probably responding to the relationship between things. And there's a nice little discussion of that. And oh my God, that's a great field guide. And the Carolina wren in the middle there. I have a bird app. I sit on the deck and identify birds, and it has recordings of songs. And for reasons I can't explain, the Carolina wren song that's on my app drives them crazy, and they fly at my head. I've been hit by their wings. They're pugnacious. And perceptual learning and Venn diagrams. latent inhibition, and was there generalization between AX and BX? That's a fairly straightforward study, and the answers are there in the last column. And there's Michael Fanzelo. As I probably already mentioned, one of your colleagues did her doctoral research with him. And that's an interesting observation, that if you shock the animal as soon as they go into the shock box, they don't seem to learn to associate the box with shock or fear. But if you let them hang out a bit and process the cues, you do. And so there's another, unitization is the third possible mechanism that can lead to perceptual learning. And acquired equivalence, there's a nice discussion here. Again, there's a design, and you should look at that, and you'll be able to see how it works. And matching to sample. So the pigeon has to peck at the white key to tell the program it's ready, and then in the second situation, that light goes from white to whatever, in this case, red. And then in the final one, the animal has to peck at matching to sample. And you can have delays there. And delays make it much more difficult. In fact, it's pretty clear they involve different parts of the brain. And conditional discriminations, and it's a nice picture of Zental, and that's a good discussion there too. And then there's another key, acquired equivalence and mediated generalization. They play an interesting role in categorization, ever larger categories, and those are nice data. The birds behaved as if they had combined two different subcategories, people and cars, flowers and chairs, into superordinate categories. So this is really quite cognitive. And as I mentioned, Skinner battled cognitive psychology. He lost. And there's a nice conclusion, and discriminability and exposure and learning. And then we get to information processing, and boy, is this cognitive. I was never a big fan of geones. This is the first time I've seen any research that makes me like it more. So geometric ions, and this is clever research. So you have the original stimulus, and then the second stimulus with or without the geones preserved, and you leave the geones in there, and the animals do much better. And this is done with computers almost for sure. 1992, possibly not. They could have been slides. But take a look at these things and the T's, and whether or not things are easy to see or not. And what's true for us is largely true for the pigeons. And there's Cook. And they not only got it right, but we could see where they were looking, which is interesting. You can't see in the animal's mind, but you can pretty much have evidence that what elements of the stimulus they're responding to. And then these are, different displays, and that are either same or different, and entropy, randomness, uh, captures visual texture, and nice research, nice discussion. And then, attention. And this is pretty amazing. Tinbergen shared the Nobel Prize with other ethologists. And here we are citing Tinbergen from 1960. And, this again reminds us of the peppered moths and the jays. And we can see evidence that if you manipulate attention, you can manipulate performance on some of these. So there are data from Blau and Blau, mixed and runs, and reaction time. Faster reaction time means better performance. So with the runs on the left, you're getting faster, and if you get a cue, you're getting faster. So that's attentional priming is relevant to that figure. And then you have working memory, and we talk about working memory and reference memory. And this is a big thing in neuroscience. It's also discussed in this chapter, like or lump it. This is delayed matching to sample, where after you see the stimulus, you have to wait. And if you make the animal peck more at the stimulus, they are less likely to show a big reduction in correct responses. So there's delayed matching to sample. So there's matching to sample. We saw that figure earlier. You peck at the white key. Second key comes up red or green, and then immediately you have to pick the key down below. But with the delayed matching to sample, after you see the stimulus, there's a pause where the animal has to, quote, mentally hold on to the concept. Okay, so here we go into some designs that I do have links on. So that's a radial arm maze, and you can see why. There's a start area in the middle, and then there's 8 arms. And at the end, there are these hidden wells where food can be hidden. This is an elevated radial arm maze because the rats don't like to fall on the floor. So you don't have to build walls. You can just bring it up in the air and ask the animal to solve this. Now, animals, rats, animals, people forage pretty automatically. And you can get at both working and reference memory here. Working memory would mean, well, the animal's going down this arm to check out this cup. And in this session, whether he finds food there or not, he's not going to go back because his working memory tells me I've been there, I enjoyed the food, or there wasn't food, and I'm going to go somewhere else. So even on day one in this environment, the animals can demonstrate working memory because they tend to go down each arm once and then just kind of hang out. Now, reference memory is do you remember what happened yesterday, the day before, the week before? And that requires training. So we talk about arming certain legs in the radial arm maze and consistently over trials, you always put food in those arms. Now, if your reference memory is working, when you're put in there, you should go to where the food is, get it, not go there again because your working memory is working until you've gathered all the food, and then you chill out. So with a trained animal, you can look at what might be referred to as short-term and long-term memory. Have I done this today? Working memory. where is the food normally kept? Long-term memory. Let's see what's on this page. And there's different ways of using this and rotating and transposing. You can do a lot of clever research with it, like with this. Let's look at some of the videos I brought for you. Let's do this one. So this is a radial arm maze. Definitely homemade. And this animal has a genetic modification that means it doesn't learn well. So there's the uneaten rewards. And the animal goes into the middle and immediately gets one right. This is a trained animal. No errors yet. And then it goes into one it shouldn't have gone in, so that's a long-term error.
Another part of the world. You may ask yourself, well, how did I get here? You may ask yourself, how do I work this? You may tell yourself, this is not my beautiful house. You may ask yourself, where does that highway lead to? You may ask yourself, am I right? Am I wrong? You may say to yourself, my God, what have I done? Letting the days go by, let the water hold me down. Letting the days go by, water flowing underground. Making a blue again after the money's gone. Once in a lifetime, water flowing underground. Same as it ever was. 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 Same as it ever was.
So that's a very clever design. I remember going back to UCLA and going into a storage room in the, it was a neuroscience lab. And in the middle of the room was a radial arm maze. And in my mind, radial arm mazes are part of psychology's history. I didn't realize that they were back and they could be used for very clever memory research. So you have long-term errors and short-term errors. And again, this animal has been trained, but it has a genetic deficit that prevents it from learning. Let me show you these other two because they're going to come up in a second, or in a minute in the textbook. So, by the way, in the book refers to water mazes. I'd prefer that you refer to them as Morris water maze because Morris is still alive and he invented the thing. So here's a rat trying to solve one where there's a queue. They just have to go to the target, climb up on it, and everything is hunky-dory. I've never run one of them, but one of your peers, the one who worked with Michael Fanslow, she did. And here's a situation. So there's the water maze. It's been the water, it's non-toxic white latex paint. And the circle indicates where the slightly hidden platform is. It's a centimeter or less below the water. And so there's the enclosure, and the investigator is going to walk in. And there goes the mouse. can't even get the animal to stay on the platform when you put him on the platform. Escape latency 2 minutes. The animal didn't escape. There's just a criterion that if it goes 2 minutes without finding the platform, you terminate the trial and you say they escaped, but they didn't. That animal would have gone all day. So these animals are getting 2 trials a day. This is day 5. So this is a well-trained animal. It does not have a genetic defect and there's no drugs on board. And that's it. The investigator doesn't even really get out of the room. The animal just goes right to the target. So Morris water maze. Originally, they used powdered milk in here. And oh boy, is that disgusting. Because when these animals get out, they shake and to dry themselves off like a dog. And they are throwing powdered milk water everywhere. It stinks. So the latex paint is a real advancement. This is modern software that we use to track behavior. We bought this years ago. Didn't use it that much. It's only $6,500. They're not giving it away. And here's a general introduction. They like themselves. So this is an open field, not a Morris water maze. And we're watching the animal explore. And orange dot in the middle of the body. But you can also get it to track the nose and the tail. You get a lot of data out of this. There's a plus maze. There's a Morris water maze. There's a Y maze. Barnes maze. I've used this one. Open field again. And very powerful software. I don't know if it's $6,500 worth of powerful software, but that's what they want. I forget what we paid. It was a long time ago. Met Associates, they're a big supplier of technology. And if you look at mazes, they have the barns, which we've already seen, circular runway, so it's a circle, elevated plus, Morris water maze, zero maze. So for money, you can buy just about anything. No surprise there. All right, so that's a radial arm maze. And they they are talking about working in reference memory and uh, retrospective coding and prospective coding. Do you track what you've just done or what you're about to do? And really cute data there from both rats and pigeons, where they seem to use one strategy and then switch to the other. People do this too. Reference to shopping lists. Early in shopping, you keep track of what you need to get, prospective, and then at the end, you're thinking, well, what's left? Did I get that right? Well, that's what you do. I forget. I don't know if I got the names right, but in the beginning, you step through what you need to pick up, and at the end, you worry about what you haven't gotten yet. And then there's different kinds of memory here: procedural, doing things; declarative, being able to say things; semantic and episodic. Some of these you can't easily do, like semantic in nonverbal animals, but these are vibrant areas of research, and this is a nice brief summary of all of them. And oh, this is so cute. So you have scrub jays, and you give them peanuts or worms, and they cache them, they hide them, and they learn that if you're going to go back and eat it soon, you go for the worm because it's more tasty. But if you have to wait for 124 hours, those worms have turned into something unpalatable. So you go for the peanut butter. The peanuts. And there's research there. Animals that cache food have parts of the brain related to that are actually bigger than normal. And there's timing, and we're going to come up on timing here later in the chapter. I'm not a big fan of this section. And there it is. So you have circadian rhythms around the day, and the pigeons can use it, rats can use it, and free running means you take away the Zeitgeber, that which tells the animal what time of day it is, and the animal just has to figure it out by itself. There's Zeitgeber, time givers, and jet lag, and that messes you up. And interval timing. Now, interval timing. The one schedule of partial reinforcement that's relevant here was the answer to the question, partial answer to the question about the first partial reinforcement schedule, which was a fixed interval 1 minute. And the pattern of responding that animals give is scalloping. So they don't respond for a while, but it's not a post-reinforcement pause. And then as time goes on, they respond more and more. So, this is timing, and temporal generalization is relevant to that. So there's distributions of responses around 2 different time intervals, and if you overlap them, they're remarkably similar. So animals can definitely use time, and regardless of the interval that is being timed, probability of responding is related to the proportion of time into that interval. Scalar property. Church was very big for me when I was early in my research on fear and pain, actually. And there's different theories of how the animals are doing this timing. And there's temporal bisection, and there's inhibition of delay, and that's a suppression ratio. And as you go towards zero, you're more suppressed. And on the right, you have the FI scallop. So different measures of time can give you very similar conclusions about animals' timing. And they're good at it. They're surprisingly good at it. And there's Church, who, as I said, was important to me. And early cognitive, not less so now, but it's still true, very influenced by computer programming. And if you've done any computer programming, you may recognize what's at the bottom of this page. So, they generated theories that turned into what looked like programs, and you have pacemakers and clocks and signals and accumulators and working memory and reference memory, and then a little bit of math and whether or not you respond. I'm not nuts for this. It's definitely it has been quite relevant, but that's way back in 1984. You don't see as much of this schematic now as we did back in the day. And there's another theory of timing where you have multiple isolators and oscillators, and you can count oscillations and figure out where you are. Sure, that's possible. And time scales and multiple time scales and behavioral theory of timing. Those are possible, and they're well discussed. And it's really a bit too cognitive for my taste, but that's the way the field has gone. And internal clocks, and it's all good. So, spatial behavior, we've already dealt with some of the tests that we use for spatial behavior. And there's different ways to navigate in space. You can have dead reckoning, you can have beacons, and we showed a video of a rat going to a beacon. So the Morris Water Maze and the radial arm maze are both going to be important for this, and landmarks. And when we do and don't use them, and we're about to see data from pigeons and people that is quite similar. And they discuss how to remove cues from around the mazes. So, landmark, single peak, primary peak, secondary peak. And humans are quite good at this on average, and Ken looks pretty cool. And now a discussion of the design of the test environment. I don't have pictures of this, but geometric module. There's a number of studies here that deal with the geometry of something that obviously is not circular typically, and how animals use these cues, and place cells. These are quite real. We now have technology where you can implant recording devices into the animals and have a little LED on the top of their heads, visible from outside the environment they're being tested in. And you can see the cells fire. You don't see the cells fire, but you see the LED lights up. And these play cells are a big deal. And it's not surprising that animals have the ability to track where they are in a three-dimensional world, or at least a two-dimensional world. And we're talking about cues that are inside the maze or outside the maze, extra maze. And I did Morris Water Maze. I did the Barnes Maze, which is that circular tabletop with all the holes around the outside. Animals, rats don't like to be exposed, and mice. I was doing mice. So one of those holes goes into like a little chamber where there's snacks and bedding, and it's comfortable and you can hide. And you manipulate cues either on or outside the maze. And there's allegedly gender differences in what kinds of cues people use. And I don't know if you've ever seen Beetlejuice, but I wanted to make a little world where I would have cues on the maze or outside the maze and see if there were gender differences in terms of what the animals would use to look at. Didn't have much luck with that. So I made that red water maze because I'd prefer you to say Morris Water Maze because Morris invented it. And, there's a Morris Water Maze in the middle of the room, and you have a hidden platform, and the tracking software can literally get you all these data. And you can have, so this is just a regular room where you have doors and shelves and clocks and stuff, or you could do things out here that are more intentional. And so there's the track, and this is what happens when you move the target, and the animal goes crazy. And there he is, Morris, 1981, 1982. And how do they do it? And then there's a discussion of different kinds of cues and which ones they're looking at. And you either can screen out the outside world or not. And obviously there's a homemade rig. I can relate to that. Tables and blinds and big ring stands and clamps. And that's the kind of thing I would make. And they're talking about how animals do in that, whether they are or are not allowed to explore the arms prior to testing. And beacons, and there's time and correct quadrant. And if you block not as much time and then more time and with no blocking or trivial blocking, you're much better at it. And curtains and room cues. So obviously I can't add to this other than having shown you the technology, and oh my God. So here you have different angles, and it's a little hard to see that thing on the right is not a rectangle. It's a rhomboid, so it has larger than 45-degree angles and shorter than 45-degree angles. And the issue is, what do the animals pay attention to? And then you have rectangles and kites in different locations, and where do you go? And so when you're consistent, you do things very nicely, but inconsistent, you get messed up. And rotational and non-rotational errors are discussed. And oh my God, metacognition. I remember when I came to Scranton, the cognitive psychologist at that time would talk about this, and it would just hurt my head as a good Skinnerian. But, again, cognitive one, and knowing about knowing. And there's some cute research, rhesus monkey, I think it's rhesus. Yeah, it's rhesus monkeys. They're put in a situation where they have to solve a problem, and they can abort and decide, no, I don't want to do this trial. And the data here are really quite compelling that the animals, to some extent, know about knowing. And there's your target, and you accept the trial, you reject the trial, and accuracy. If you accept, your accuracy is good, and when you decline, it's not so good with it's not so good if the animal decides to decline. So they seem to know when they have a good grasp over whether things are going to go. And the longer the delay interval, the harder it is to hold things in memory, and the more likely you are to decline the trial. And different kinds of discrimination and timeouts. How do they do it? Is as they point out, and this is what made Skinner uncomfortable, because now you're dealing with theoretical constructs that you can't easily see. And one problem with this approach is that it does not really explain metacognition. It's a bit circular. Of course, Skinner is circular too, but he's not trying to be theoretical. And the results with meta-memory are most consistent with the idea that although rhesus can learn to report on the strength of their memory, learning to pair strong and weak memory states with two different responses would proceed according to accepted associative principles, in other words, not magical. And the old principles of learning before cognitive haven't gone away. They're still there. So what do you got to know? You have to be able to describe these things, take a look at the videos. What is a Morse water maze? What's a radial arm maze? The kinds of things that training can produce in animals are pretty amazing. Pigeon bombs, anti-tank dogs, fire bombs. I'm really impressed with the bomb sniffing and TB sniffing rats, and possibly cancer and COVID sniffing dogs. And there's Morse water maze, cuter, relatively unusual, but normal is more common. And there's radial arm maze with an animal who basically cannot learn and is making both kinds of errors, working errors and reference errors. And remember, in a radial arm maze, if you only go down an arm once, your working memory is probably working. If you only go down the arms that typically have food, your working memory is working. So you can differentially destroy working and reference memory. And you may have working or reference memory that's intact, and you only go down the correct arms, But if your working memory is gone, you go down them over and over. It's incredibly clever. So lots of stuff. It's a fairly straightforward chapter. It is an open book test, and you can access these links. I've been having trouble getting my software to record audio from videos. Let's hope this is not one of those problems. And we're